In today's video, we're going to be making power series, as well as doing calculus on power series. And in order to make a power series, we need to recall our geometric series formula, which is the infinite sum from 0 to infinity of a times r to the power of n, which is also in the form of a over 1 minus r. And remember, our radius has to be less than 1, and I meant our absolute value of our radius has to be less than 1. And this is typically used to write a function as a power series, which is typically in 1 over 1 minus x form. And the reason we do this is later on we're going to do Taylor series and Maclaurin series, where we use this to find our Taylor series for our function. And then in the second part of this video, we're going to do calculus on power series. And if you recall, we're just going to differentiate, which is just finding the derivative. And so if our f of x is equal to a of n times x minus c to the power of n, then our f prime of x is just going to be n times the a of n times x minus c to the power of n minus 1, which is just a typical differentiation form. And then for integration, we just find the integral of it. And that's basically been the beginning of calculus 2, so hopefully you remember how to integrate. And so let us begin. Now let's let the first problem be to find the power series representation of f of x equals 1 over 2 plus x, and find its radius and interval of convergence. Now, the very first step you want to do when you're asked to make a power series representation of a function is to make sure you put the function, which is 1 over 2 plus x, into the form a over 1 minus r. Now, you might be wondering, how do we do that? This isn't a 1, and this is a positive and not a negative. Well, what you can do is in the denominator, just factor out the 2. So it becomes 1 plus x over 2 times 2 over here, all while being under 1 still. And then next, try to take out that 1 over 2 by just simply multiplying it by 1 over 2 times 1 over 1 minus negative x over 2. Now the reason we did this negative was to make sure we fit the form of the negative over here. So this is just the same exact thing as adding over here, because it's just a negative and another negative. Now where people get confused the most is, and by people, this is just personal experience, is that this top number might be confusing you because you might think, oh, our a is just 1, but it's not. Our a is actually this 1/2 over here, because this is just the equivalent of saying 1/2 over 1 minus the negative x over 2. So in this form, our a is 1/2. Now we also know our r because it's over here. It's negative x over 2. And so again, we're comparing this to the form a over 1 minus r. Now that we have our step 1 out of the way, which was to convert into this form, let's do our step 2, which is to plug in our function into our series form, which if you recall is from 0 to infinity of a times r to the power of n. And what makes it so easy is all we do is just plug in the variables we found over here. So our a was 1/2, multiplying by our radius, which is negative x over 2 to the power of n. And again, don't forget our summation. Now we could simplify this even further by recognizing that this is the same exact thing as 1/2 times negative 1 times x over 2, all to the power of n. Now this is important to separate the negative 1 and multiply it, because this is also going to be included in our nth term. So again, simplifying further, this becomes the series from 0 to infinity of 1/2 times negative 1 to the power of n times x to the power of n over 2 to the power of n. Now, to simplify even further, remember that 2 times 2 to the power of n is exactly the same as just doing 2 to the n plus 1, because we are just multiplying itself again. And in this series, if we just add another 2, and what I mean by add is multiply another 2, we are adding another term. So depending on your professor, I'm not sure how picky they are about that, but I think mine is. So just be safe and write this as the infinite series from 0 to infinity of negative 1 to the power of n times x to the power of n over 2 to the power of n plus 1. Sorry. Now are we done? No. We only found the power series representation, which is given here. So let's find its radius and its interval of convergence. Now we already found our radius, which was negative x to the power of 2. So we could say our r equals negative x over 2. But remember, in our notes over here, we want to make sure that the absolute value of that radius is less than 1. So we're going to plug in that formula over here into this r. So it becomes the absolute value of negative x over 2 less than 1. Now we can just remove the negative sign because it is an absolute value, and then just do algebra from here, which then states that the absolute value of x is less than 1. And then we could do algebra from here, where we just multiply 2 on both sides. So then this finally states that the absolute value of x is less than 2. So this r is not the radius of convergence where it states negative x over 2. Our actual radius of convergence is 2. right here. So to find our interval of convergence, we just subtract this, we just put this 2 to the left side and make it negative. So then this states that -2 is less than x, which is less than 2, which then leaves our interval to be -2 to 2. Now typically we would test this like in a normal power series, but with a geometric series, remember this, we will always have parentheses at our endpoints because we will never include these numbers. So therefore, we don't have to test anything. Now again, if this was a typical power series, you would want to test it to see if it would be brackets instead. But because we are for sure we came from a geometric series, our interval of convergence will just be not including these numbers. Therefore, it's a parentheses. And our radius of convergence is going to be r equals 2. Now let's move on to the next question. Now, banking off of the original function in the first problem, let's let our next problem be that given f of x equals 1 over 2 plus x, find the power series for g of x equals 1 over 2 plus x squared. Now, you are given a choice of whether you integrate or differentiate, and in this case, you would assume to differentiate, which is taking the derivative of, because this is the equivalent of 2 plus x to the power of -1, which if we were to take the derivative of it, we would get -2 plus x to the power of -2, which is equal to -1 over 2 plus x squared. Now the conclusion you can come up with is basically this g of x is equal to the derivative of f of x, but not just the normal derivative of f of x, but the negative derivative, considering there's a negative sign in front of the function. Now what to do next is you would typically differentiate the series given from f of x to equal 1 over 2 plus x in this case, which we already did in the first problem, which we found out was this. So again, this is just our f of x function in series form, so let's try to find the f prime of x in this series. Now note that we cannot start at 0 in this case, because if you were to plug in 0, you would end up getting a constant, which is 1/2, which you do not want. So instead, we're going to start our series at n equals 1 to infinity. And then we could put the derivative symbol alongside our inner function. Now don't be worried about this n being 1 changing anything in the inner function. The only thing that changes is that we have a derivative symbol inside, so that's what that's accounting for. Now, this is a very important thing to notice. Since we are taking a derivative of an x term, we are not going to mess with any of these terms here, and I meant to include that n over here. We will only pay attention to this x to the power of n. So what's going to happen is our series is still going to be n equals 1, and we're still going to have the -1 to the power of n over the 2 to the power of n plus 1, but this time we're going to take out this x to the n, since that's the one we're deriving, and just doing a normal derivative on it, which you put the power term into the front, and then multiply by x to the power of n minus 1. And that's just a basic power rule in differentiation, so that's how I ended up getting this. Now remember, this is our f prime of x, and what we're looking for is our g of x. So, in order to satisfy this entire statement, since g of x does not equal the normal f prime of x, it equals the negative f prime of x, we're going to have to multiply this entire thing by -1. And remember from earlier, if we multiply this numerator, or if we multiply the denominator by like -1, or I mean 2 in this case, since it is the same exact term as this -1 over here, this is basically just adding on to the series. So this would end up being the infinite series from 1 to infinity of -1 to the power of n plus 1, since this -1 absorbed into this -1, over 2 to the power of n plus 1 times n times x to the power of n minus 1. Hopefully that makes sense. And I apologize, this is now the g of x, not the f prime of x, because this is technically equivalent to the negative f prime of x. Now what we're going to do is called re-indexing the series. So we want to make sure it starts at 0 again, since that's what we originally had it in. And now, since we're starting at 0, these power terms are going to actually be affected this time, unlike this one where none of the terms were affected when we changed the index to 1. So what ends up changing? Well, every single n is going to be added to 1 when it comes to being raised to a power. This n does not get affected. So we end up getting g of x equals the infinite series from n equals 0 to infinity of -1 to the power of n plus 2 over 2 to the power of n plus 2 times n times x to the power of n. Now we can also further simplify, because -1 to the power of anything will just stay the same as it always will. So the -1 could just be to the power of n by itself. And we can move this right side, which is the n x to the power of n, inside our function again. It means the same exact thing, but it just looks nicer. Now, again, we are not done because I may have misspoke earlier and said that this n does not get affected, but it does. I apologize. So our final answer is going to be the g of x equals the infinite series from 0 to infinity of negative 1 to the power of n times n plus 1 in parentheses times x to the power of n over 2 to the power of n plus 2. And that is our final answer. Now let's let our last problem be to find the power series for h of x equals ln of 1 plus x by integrating the geometric series for 1 over 1 plus x. Now the first thing you want to do is to find the geometric series for 1 over 1 plus x, which again is the form a over 1 minus r. And to put our 1 over 1 plus x in that form, all we have to do is just change that x into a negative x, but to maintain its positivity, we have to subtract as well. So it's going to be 1 over 1 minus the negative x. Same exact thing as 1 over 1 plus x. And now with this form, we know our a equals 1, and our radius equals, and our r equals negative x, which is the common ratio. I apologize if I keep saying radius. Now all we have to do is put the series from 0 to infinity of negative x to the power of n, because we multiplied the 1 and the negative x. But remember, this is the same exact thing as multiplying by negative 1, so this is actually negative 1 to the power of n times x to the power of n. Now we're going to want to set our h of x, which was ln 1 plus x, equal to the integral of the series from n equals 0 to infinity of negative 1 to the power of n times x to the power of n dx. Now, just like differentiation, we are not taking the integral of anything in these terms because there is no x. So this just ends up becoming 1 plus x inside the natural logarithm, which equals c, the constant of integration, plus the infinite series from n equals 0 to infinity of negative 1 to the power of n times the integral of x to the power of n, and then of course our dx. Now this is just a typical power rule but for integration, so this just becomes the natural logarithm of 1 plus x equals the constant of integration plus the infinite series from 0 to infinity of negative 1 to the power of n times x to the power of n plus 1 over n plus 1. Now what you want to do now is find this constant of integration simply by just setting x to 0. Now when we do that, this just becomes the natural logarithm of 1 equals c plus 0. So our constant of integration is 0. Now to fully represent the function, we just set our h of x, h of x to the natural logarithm of x plus 1 equals, and then the series we found, which is 0 to infinity of negative 1 to the power of n times x to the power of n plus 1 all over n plus 1. And if our constant of integration was anything but 0, we would add that here. Let's say if it was 3. But ignore that because our constant of integration is 0, and adding 0 is pointless because it's nothing. And that will wrap up our video. Have a blessed Thanksgiving.